Okay, now that we've got a handle on the formula for DeMoivre's theorem and where it comes from, let's apply it for a particular complex number and determining what raising that complex number to a power, say 5, is. So we've got this complex number, -1 plus root 3i, and I want to raise it to the 5th power. Now, before we had DeMoivre's theorem, what we would have to do is we would have to write this all out. It's a bunch of -1 plus root 3i. It's 5 of them, to be precise. -1 plus root 3i, -1 plus root 3i, -1 plus root 3i. That's 3 of them. Got 2 more. And -1 plus root 3i, that's 5 of them. So in order to multiply this whole thing out, you just kind of go down the line, multiply these guys together, that gives us another binomial, multiply these guys together, that gives us another binomial, multiply this together, and that gives us another, etc., etc. And we work our way down the line, simplifying as we go. It gets really tedious to do this, and it's easy to make algebra errors along the way. I don't recommend foiling this all out. We can do it later to just check our answer. But there's a much quicker and faster way to do that, and that's using DeMoivre's theorem. So first step in DeMoivre's theorem is I need to get my point into polar form. So step 1 is to calculate the magnitude of z, or the absolute value of z. And that's going to be equal to -1 quantity squared plus root 3 quantity squared, all taking the square root. It's the distance z is from the origin. So this is root 1 plus 3, which simplifies to root 4, which is 2. So it's got a magnitude of 2. Next up, we calculate the angle. Theta is the inverse tangent of b over a, which is negative root 3 over 1, which is the inverse tangent of negative root 3. If I remember my unit circle well, this is a nice number you can take the inverse tangent of on the unit circle. And it's going to have 2 answers, if you think about it. Negative root 3, that's my slope is negative, and it's steep-ish, root 3. So this one is going to be this angle and this angle. This is negative pi over 3, and this one up here is 2 pi over 3. So let me see if that's, yeah, that's showing up there. So these are my 2 angles for this. Let's figure out which one we want. I have a negative real part and a positive imaginary part. This one's positive real, negative imaginary, real, imaginary. This one's negative real, positive imaginary. This is the one I want, is I want this point right here. That's z. On the second circle of radius 2, actually. So it would be r equals 2. That's where z is hanging out. So this angle is 2 pi over 3. Okay, so let's plug it in. Okay. So that says that z equals 2 cosine of 2 pi over 3 plus I sine 2 pi over 3. Let's just double check that's visible. Okay. So this is my polar form for it. So let's raise this z to the 5th power. Do this in blue now. So we're going to do z to the 5th, which is, oh, I lost my, yeah, no, that's 2. It's always a good idea when we're doing things with z's to write the slash in the middle so you don't confuse a z and a 2. Now my z and my 2 look very similar, it's just that the 2 is doesn't have the bar in the middle. That's why this bar is in there. Okay, so we've got 2 to the 5th power, and then DeMoivre's theorem says we raise 2 to the 5th, and we multiply the angle by 5. So we've got 5 times 2 pi over 3 plus I sine 5 times 2 pi over 3. And we just multiply the 5 and 2 and get 10 pi over 3 for both of these. We've got a little bit more work to figure out what that is. So 2 to the 5th is 2, 4, 8, 16, 32. 32. And then cosine of 10. So we've got cosine 10 pi over 3 plus I sine 10 pi over 3. And we have to go back to our unit circle and think about what answer that's going to be. Where's the cosine, or what's the value of cosine when the angle is 10 pi over 3? So let's draw our unit circle. How many times around the circle do we need to go? We might have to go a couple times around the circle. Let's find out. Okay, so this would be, I'm going to break it up into thirds. There's pi over 3. This one's 2 pi over 3. 3 pi over 3. 4 pi over 3. And 5 pi over 3. And then back here is 6 pi over 3. Or 2 pi. So let's keep going. We need to get to 10 pi over 3. So here's 1. So this is 7 pi over 3. 8 pi over 3, 9 pi over 3, 10 pi over 3. So this is the same point, 10 pi over 3, same angle. My cosine over here is going to be negative 1/2, and my sine is going to be negative root 3 over 2. So we can enter those numbers in here. So this is equal to z to the 5th is 32, and now we've got negative 1/2 from the cosine, and negative root 3 over 2 from the sine, I. And we just distribute the 32 through and we're basically done. So we take 32 times negative 1/2, which is negative 16. And 32 times negative root 3, I is negative 16 root 3I. And that right there is z to the 5th power. Not too bad. Required us to really delve into remembering the angles on the unit circle, but as long as we know the unit circle really well, it's relatively straightforward to calculate any power of the complex number, as long as this complex number has got a nice point on the unit circle. Of course, if this doesn't end up falling on one of those nice angles in the unit circle, you'll have to use your calculator to determine the angle, but the same thing's going to happen. You'll still find this angle, whatever it is, and multiply it by 5. Take the cosine, take the sine, and that's how you'll find your real and imaginary parts. Okay.